Hey guys, welcome back to chemistry for the rest of the semester. Today we talked a little bit about the atomic theory a little bit more and got some more clarification. We ended up today in class talking about Bohr and Bohr's discovery, and then we realized something was not quite right about Bohr. So because something was not quite right about Bohr, we have to come up with another portion of the theory, and that's where this goes today. So here we go. Today we were going to talk about the quantum or wave mechanic theory that was born in the mind of Erwin Schrödinger. Here we see Erwin Schrödinger, a picture of him, and we know that Schrödinger applied the ideas of electrons behaving as a wave, which was a new concept. Remember, we talked about how Bohr had done some Newtonian physical concepts and really looked at it from a macroscopic Newtonian physics level, and we realized with Schrödinger's discovery that we can't deal with an electron that way. It's not a particle like a box sitting on a floor. It has to behave differently, and so we have to come up with a new set of ideas for that. And in this case, we see that the wave behaves like, or the electron behaves like a wave. So he developed something called a wave equation. And the wave equation, boiled down, looks like this. And what we see here is basically an equation that gives us this idea that we have, this is the wave equation, psi represents the wave equation. This talks about position and this talks about the energy of the wave or the speed of the wave. And so that's kind of breaking it down into simplistic form. However, when we look at this in a more direct form, it's much more complicated than that. And solving it is much more complicated because you need calculus. So we go further to talk about the fact that the solution gives a set of mathematical expressions called wave functions, or this psi. Once we get the wave function, we know more about the electron. So each describes an allowed energy state of the electron. So basically, we're finding information about a specific electron. We're coming up with a very specific set of information that's going to tell us more about that electron. So the Heisenberg uncertainty principle tells us a couple of things. Heisenberg, along with Schrödinger, came up with some more ideas about the quantum theory. And what Heisenberg says is that we cannot define everything about the electron. What we can do is we can either define the position or we can define the momentum, but we cannot define both at the same time. We define energy exactly, but we're limited to knowing the position. So if we know the position, we don't know the energy. If we know the energy, we don't know the position. It all comes down to that idea of Schrödinger's cat that you've talked about. If I'm sitting in this classroom, empty classroom, and there's a cat roaming around and I'm sitting here blindfolded, and I can begin to start throwing balls to try to find the cat. Well, I'm hearing balls ping off the wall, but eventually I hear a meow, and I've just discovered the cat. I knew where that cat was, but I don't know what energy the cat has. I don't know what direction it went into, so I can only know a certain amount of information about the electron, just like the cat. And that's called the Heisenberg uncertainty principle, being uncertain about, you're certain about some things, but not certain about other things. So this boils down to this. We're coming up with some quantum numbers. This equation gives us quantum numbers, and there are three that the equation gives us. It gives us the shape, the size, and the energy of each orbital and function of three quantum numbers. Basically, these are the quantum numbers. N, which is defined through the equation, is the energy level. How much energy does it have? Does it have low energy, high energy? We can define the shape of the orbital. What does the orbital look like that it can contain in? What shape would this electron be in? And finally, it designates a particular way in space that it's arranged. So the suborbital is talking about the arrangement in space that it has. Now, there's a fourth one that was not derived by the wave function. The fourth one not derived by the wave function was defined by Pauli a little bit later on, because Pauli said some things that we'll talk about in just a minute, and that is called the spin. So we can have 2 electrons per orbital. That means one spins one way, one spins the other. Otherwise, matter would collapse upon itself, because everything would be spinning in the same direction, and eventually it would fly apart because there's just way too much energy going on. So they have to balance each other out. So it boils down to this. Electrons and atoms are arranged as energy levels is the first arrangement that we understand. That's the basic. Then we go to sublevels. And after we understand sublevels, then we get a little deeper and we know the orbital that it lies in. So notice we're getting information. They'll like general information, and then we go to a little bit more specific, and then we get even more specific, and finally we get to the most specific that we can get. Now this relates to something else. So when we look at this, we see that this is where we talk about Pauli. Pauli talked about the electrons, and this is where the fourth quantum number came from, because Pauli said that no two electrons should have all the same quantum number. So we had to come up with a fourth one to distinguish between the two electrons within an orbital. But the most important thing that Pauli said is right here, this statement right here. Think of the quantum numbers as an address for the electron. What country is the electron in? What state is the electron in? What city is the electron in? And what street is the electron on? So if we think about it in that way, it makes a little bit more sense to us. We're getting more information. So the basic information, what country, where? What state gives us even more? What city gives us even more? And then finally to the street, we can begin looking for that particular electron, even though we're not going to know all of the information. So if you think about the quantum numbers, NL, M sub L, and M sub S, as the address of the electron, that might help you get a little bit better of an understanding. So energy levels here. Each energy level has a number. Okay, those numbers are designated by some information that we need. Currently, N can be 1 through 7 because there are 7 periods on the periodic table. So we see that there's energy level 1, and energy level 1 is here to here. Energy level 2 is here to here. Energy level 3 is right here. Now there's a little problem in energy level 3, and we'll get to that in just a second. This is where the system goes haywire, right in here, because something happens right here. This is actually part of that energy level. So this portion right here, let me get a different color. This portion, no, not a good color there. Hang on, let me get one that's going to show up. This portion right here through this portion right here is going to be n equals 4, but so is this. And then we kind of get haywire. So some things go wrong when we hit that D block. But what we do need to recall is all representative elements. Now, let's look at representative elements really quickly. All representative elements, that's these 2 columns and these 6 columns right here. They all have an N that is equal to their period number. Always. Okay, nope, I'm sorry, period number. So we just have to make sure that we understand that. N is equal to the period number if you're a representative element. All right? So orbitals take on different shapes, and this is where the L comes from. So we have these different shapes of orbitals. In the next few slides, you're going to see not only L, but M sub L being described. Now, the 4 shapes we have are S, P, D, and F. Now, I'm not sure exactly where those names come from. I know that S is a sphere, but that's as far as it goes, because P's start to be dumbbells, and D's get double dumbbells and a donut. I mean, there's some crazy names. So only 2 electrons can be assigned to a single orbital. One spins up, one spins down, or one spins clockwise, one spins counterclockwise. So here we are. This is the S orbitals. Notice they're spherically shaped. They're shaped like spheres, but the 1s is smaller than the 2s, and that's smaller than the 3s. So as we go up in energy level, the amount of space that an electron can occupy goes up as well, because that electron is probably going to contain more energy. So the space that it occupies is going to go up proportionally to the amount of energy that we have. So there is the S sublevel. Now, p orbitals look like dumbbells. So if you can see this, you see one side and the other side. So it's like you've got dumbbells next to each other. So this is a p sublevel, and it has 3 separate orbitals. They're called py, pz, and px. And so what we see here is there's the p orbital. There's what it looks like. It looks like this kind of figure 8, and the node, or the place where the nucleus is right there, is the planar place. So you have one of these in each place. So that's called a planar node. You don't have to worry about the planar node. All you need to know is the basic shape of a p orbital. Okay, so there are all the p orbitals. Here is the px Notice it's along the x-axis, the py is along the y-axis, and the pz is along the z-axis. So these are the three shapes and orientations that are the p. So when you see them together, you're basically going to see lobes this way, and lobes going up and down in a three-dimensional setting. And I might show you one of those tomorrow just to give you a better idea. Okay, the three orbitals are aligned at 90 degrees apart in space so that there's plenty of room for the electrons. D orbitals get a little bit crazy. I can't show you D orbitals in class, but you're going to see some craziness. It has 5 orbital sublevels. And remember, these orbitals are spaces that the equation defined. The equation defines these spaces. The equation gave us these spaces, and they're the probable space that the electron should be in 90% of the time. So that's where these spaces come from. So we see a d orbital. So d orbital looks very similar to a p, but notice that there are 4 lobes instead of just 2. And you have another planar node here that goes between the planes. So this is what a d orbital looks like, generally speaking. Now there's one that looks weird. So here we go. Here are the d orbitals. So you can see there's 1, 2, 3, 4 that look exactly the same. And then this dz squared, this crazy one that's along the z plane, looks like a dumbbell like the P, but then it has a donut around it. And we literally call that a dumbbell with a donut. Now, if the D's got more complicated, the F's are really going to get more complicated. So F's, notice, have 6 lobes instead of just 4 lobes. So for L equals 3, the F sublevel has 7 orbitals. Now down here, this one is very special. You notice all of them have 6 lobes. They're doing really a strange, good thing. And then this one gets really strange because we have this dumbbell on the z-axis, but it's got a double donut around it. And we literally call that the donut with a double dumbbell. That's a literal name for it. So now we're going to talk a little bit about filling, and I'm going to stop this one and I'm going to actually make another recording, so we'll come back to this in just a second.